All right, guys. Today we're going to start thermochemistry, and this is normally a chapter that's way towards the back of the book, but I think it's important that we talk about it at this point because if I wait till the end, one, we may not get to it. Number two, I think it's going to help us understand a lot of the stuff we're going to get to towards the middle of the year. And so I go ahead and throw it in here at the very beginning. Secondly, I normally do this in the middle of chapter 1, but this year I've backed it off. I'm going to do it at the end of chapter 1. So we will still have a test on that entire packet. Some of those questions you've already seen, some of the questions you've already done, some of the topics we've already covered. But this is the part that I want to go back and I want to hit the high points of all this, and then we'll have another test. So this will be the second test, or the first test we do in this 9 weeks. So let's go ahead and start by understanding what thermochemistry means. So what does thermo mean? Okay, let's go with heat. Or we can say heat exchange. Okay? And there's a difference between heat and heat exchange. What does exchange mean? To switch, to swap, to give. Essentially, is it moving? Yes, okay, that's the key. Heat is going to be moving constantly. Okay? So that's the thermo part. Heat or heat exchange. Chemistry. Yes, some of you are sitting in here. Some of you aren't taking it really well, but you're sitting in here. Never mind. Okay, so what is chemistry? Did y'all get that at all? You're sitting here, but you're not taking chemistry really well. Means your grades aren't that great. Oh. What is chemistry? Science. It's not depression. Okay. All right. So let's simplify. It's the interactions of atoms and molecules. The interactions. Interactions. There are a lot of things we can talk about as far as interactions. Oh yeah. Talking about structure, functions, properties, all that good stuff. Thermochemistry basics. Now the basics means we're not going to get into the depth that we normally go. If any of you decide to take AP, which I want several of you to do, we'll spend an entire unit on thermochemistry, and you'll learn the depth of it. We're going to just kind of hit the high points. So, thermochemistry is we're going to talk about the heat and heat exchange of atoms and molecules. So, we're going to talk about 3 major things in this topic. We're going to talk about endothermic, exothermic, and specific heat. Those are the 3 main things we're going to look at in this little chapter. So, the first thing we need to talk about is enthalpy. Okay? Now, I'm going to talk about what enthalpy is, and then I'm going to sing you a song. Okay, so the first thing is we need to know what letter represents enthalpy. So when you see that letter, you know that means enthalpy. So instead of writing the entire word Fahrenheit, what do you write? F. Instead of writing Celsius, because I can't spell it, what do you write? C. So instead of writing the word enthalpy, what letter do you write? H. Now I get it. We get why F is Fahrenheit, why C is Celsius, why K is even Kelvin. But why is enthalpy H? I understand the question, okay? There are certain letters that have nothing to do with the word itself. Now, some of you are saying, well, there's an H in enthalpy. Duh, dummy, I get that. Well, that may have something to do with it, may not. And enthalpy can stand for some sort of heat thing. And yeah, that's fine and well. But just know that it doesn't always make sense. We're going to get to a letter in the back of this little section, the letter Q. And the letter Q has nothing to do with the word that it means, okay? So don't get grasped and hooked on the fact that the letter has to have something in common with the name, okay? So the letter H stands for enthalpy. Now, what is enthalpy? And this is the definition. It says it's the measure of the total energy of the system. Now, the system versus the surroundings. What is the system? The total energy of the system. Okay? Here's what the system is. The system is the atoms and molecules. That is the system. Do you agree that that is what is doing the energy exchange? Yes. Well, then the next question is, what is the surroundings? Say that again. What'd you say? Everything else. Is that what you said? That's what I thought you said. That's why I asked you to say it again. So the surroundings are literally everything else. So can atoms and molecules exist in a beaker? So what would the beaker be? Everything else. So a reaction can take place in a beaker. Can it be on a beaker on a table? A beaker on a table in a room. A beaker on a table in a room in a school. A beaker on a table in a room in a school in a city. A beaker on a room on a table in a school in a city in a state. A beaker on a table in a room in a city in a state in a school in a country. Like, all of those things are your surroundings. I did. Now, the point is that do some reactions affect the entire universe? If I light a match, can somewhere in New York City fill that match? No, most definitely not. But are there some reactions, do they affect the entire universe? If a star explodes, what happens? It affects everything, right? So what happens, your system can affect your surroundings. So let me go a little more small scale. If we light a match, it probably is not going to warm up the room next door, nor will it warm any of you. But if I go to get to the gas station across the street and drop a match, we're probably going to feel it, right? Okay, that's a much bigger impact. Go to Japan and ask Nagasaki and Hiroshima how they feel about impacts. In fact, if you research those two cities nowadays, they're beautiful, they're flourishing, they're wonderful places to live, other than the fact that you probably have a third arm growing out of your head. No, I'm kidding. All that stuff's gone. But the fact is that a reaction occurred. Now, whether it be as simple as lighting a match or an atomic bomb was set off, the surrounding was affected. And sometimes the large surroundings are affected and sometimes they're not affected at all. But that is what enthalpy is. Now, so let's talk about the basic definition of enthalpy. I encourage all of you today to find one person who's had this class before and ask them what enthalpy is. And I can assure you they will tell you they know because of this little song. Now, I do not profess to be a wonderful singer. In fact, I'm terrible at it. But I can sing this song because it's 3 words. And so here's what enthalpy is. Enthalpy is energy. Platinum hit, right? Okay. So, what is enthalpy? It's energy. What does energy mean? It's the exchange of something. Okay. It's hard to define energy. If I said define it, it's really hard to define. Is energy something you can calculate? Is it something you can quantify? Yes, all those things are true, but can you hold energy in your hand? Can you drink energy, not in a form of something that's going to give you a heart attack? Okay, all of those things have to kind of play into the system of what enthalpy is. So, what is enthalpy? Energy. All right. Now, you'll never just see the letter H. Okay, the letter H will always have a triangle in front of it. So the term enthalpy will always be seen as this. Now, what Greek symbol is that triangle? Delta. So we say it, not triangle H, but what? We say it as delta H. And here's the reason why. We've talked about this before. What does delta mean? Change in. It's right there in green and underlined. So circle or highlight that phrase right there. The reason we don't just say, well, there's your enthalpy, is because what is energy constantly doing? Changing. What can it never do? Be destroyed or created. So energy is constantly going back and forth from something to something else. So we can't say, here is the energy, because does energy ever stop? No, it's constantly going. So we're trying to figure out the change in energy. Therefore, delta H means a change in energy or a change in the energy of a system. And again, we're focusing on the system, which is the atoms and molecules. I'm not really necessarily all the time worried about the surroundings. Yes, can the surroundings be impacted? Absolutely. But for the most part, we're trying to figure out what the system itself is doing. Now, you've already told me it can't be created, it can be destroyed. I told you this several days ago. There are 2 ways energy is viewed upon. What are the 2 things energy can do? It can either be blank or blank. No. It can either be absorbed or released. Very good. Now, that's common sense. You either add energy or you let it go. It either comes in or it goes out. Okay? Now, mathematically, ladies, if we're talking about absorption or release, can you assign a sign to that? I know that kind of sounds weird. Can you give it a positive or a negative? Yes. So the change in energy can be a positive or a negative. Now let's think common sense. If energy is absorbed, what would you expect the sign to be for that? Positive. Well, duh, that makes sense. So let's come in and let's add a positive right there. So absorbed is going to be a positive sign. Okay, and you can write this outside the boxes. You don't have to cram it in where I'm cramming it in. Well, what's the alternative? If energy is released, what do you think that sign's going to be? Negative. We'll keep that in mind because we're going to come back to those two small topics that I think is important. So we've already defined system as atoms or molecules, but down here at the bottom, you probably didn't see this. It says the system is a scientific name for a chemical reaction or a physical process. Is there a difference between a chemical change and a physical change? What is a physical change? That's an example. What is it? That's okay. No, that's fine. Okay. Does it change? Hang on. Jackson, what you got? Okay. The substance that it is composed of is not chemically broken down and changing its chemical composition. It's still the same thing it was when it began. Now, you said, what was your example? Grayson, what was your example? Melting, okay? When you say melting, what's happening specifically? Okay? Is it still that substance even though it melted? Yes, okay? So that's kind of what we're talking about. Now, chemical reaction, throwing you a curveball. How many signs were there to tell you a chemical reaction occurred? 5. By raising your hand, somebody give me one. I'm going to call on you. Chloe. Oxidation. Give me the common name. All right, that's for what element? Which? That's it? Iron. What does silver do by common name? Anybody? Tarnish. Silver tarnishes. Okay. Avery, another one. Color change. That's 2. Bubbles. Go ahead. Heat and light. Hayes. Everyone always forgets the last one. Solid precipitant. Very good. So color change, heat and light, precipitant, bubbles, and oxidation. Those are your 5 signs of a chemical change. Now, which one do you think we're probably going to be dealing with in this particular topic? Heat and light. Very good. So that's what we're kind of focusing on. Is it only always heat and light? Could there possibly be some of the other ones? Sure. Absolutely it can be. All right, so let's talk about the signs of delta H. And this is something we've already talked about. We just want to add a little bit of depth to it. So the sign of delta H, before I go any further, delta stands for what? Change in. H stands for enthalpy. And what is enthalpy? Energy. Again, ask somebody today if they know what enthalpy is. So if the sign of delta H is positive, again, you've already told me that that system is gaining energy. What's another word we can say for gaining? Absorbs. Okay, so it brings it in. It pulls it in. Well, obviously, if you add stuff to you, what's going to happen to your weight? It's going to go up. You're going to be gaining. Now, here's the new word you need to know. Okay, if it is positive delta H, we have a special name for it. What is that special name? Endothermic. And what does endo mean? Thank you. Within or inside. Okay? Within or inside. So endo means within or inside, and thermic is obviously heat. So it's heat going inside or within. Now, how can you tell physically? Remember, for chemical reactions, there has to be some sort of physical component for us to be able to see or feel or have an effect upon. Cody, what are you doing, dude? Gotcha. Okay. So if it's endothermic, you may not see bubbles, you may not see a color change, you may not see oxidation, but you may have a change in heat or light. Because remember this, sometimes these are chemical changes. So if it's endothermic, what happens to its temperature? It gets cold. Now, here's the deal with the word cold, and when we talk about heat up or hot in just a second. Those two words are arbitrary. What is the definition of arbitrary? They don't mean anything. Okay? Here's why. Heat or hot and cold or cool is all based on perspective. Okay? When you're hot, I may be cold. And when I'm cold, you may be hot. Some of you are very cold-natured. You would rather be cold than you would be hot. I'm the complete opposite. I would rather be burning up than freezing cold. Again, some of you say that's crazy, that's ridiculous. Some of you like fruit, some of you like vegetables. We have that ability to have that opposite effect. So cold and hot or heat up is all arbitrary. It does not mean anything. Again, because what you feel is cold or hot is completely opposite to me. Now, are there some thresholds to the human organism, again, we're an organism, that can affect whether something's hot or cold? We can't live in a volcano, nor can we live outside in Antarctica. But are there organisms that can do those things? So again, hot and cold is arbitrary, but it can be quantified. And what does quantified mean? Quantified. Has numbers. Okay? You can give it a value, and values can be used to compare it. Because if I said if it's a specific temperature, is it easier to compare to? If you just say it's hot, well, it may be hot to you, but it may be perfect weather to me. Okay? If when you got up this morning, if I was driving to school with the top down on the Jeep, it was 56 degrees. Some of you would have said, that's really cold. Some of you said, that's perfect. It all depends on how you feel. Okay? So, that's a positive delta H gaining energy. We're going to call that thing endothermic. Keep this name in your vocabulary. It is not going anywhere. Endothermic. What happens if the sign of delta H is negative? Well, first of all, it's losing energy. What's another way to say losing? Releasing. Okay. And if it is doing that, if we can see our delta H is negative, we're going to call it what word? Exothermic. And what does exo mean? The exit or outside, like an exoskeleton. Okay? To exit or the outside. So it's leaving wherever it began. Now again, physically, how could you know that? What is it doing? It's heating up. And again, those things are going to be arbitrary. What we would say is a big change in temperature may not be. It could be very small, but it could be very impactful. Okay? So, tying them together. This is just kind of one of those things. We're putting the exact same information on the same slide so you can compare it. So, endothermic. The system gains energy. This is another way to view it from a quantitative standpoint, that delta H is greater than 0. What's another way to say greater than 0? Positive. Does that make sense? Okay? It arbitrarily gets cold. And then the big one, the new one, put a star beside this, is non-spontaneous. What does non-spontaneous mean? Okay? And I like what you said, Mason. It doesn't do it randomly. It doesn't just naturally happen on its own. Write this word for me. Oh my gosh. It requires, and capitalize it just like I did, lots of energy. Okay? It requires lots of energy. And we're going to quantify that in just a minute. Now again, what do I mean by quantify? We're going to give it a number. Another one-word thing you can write here is that it has to be forced. Okay? It's not going to just magically happen on its own. It has to be forced. So it's requiring a lot of energy. Okay? So let me give you an example. I know most of you know this. I'm just going to ask it. Y'all know the hill down there by the softball field going up to the football field? Some of you have ran it several times. My question to you is, if I was standing at the bottom of that hill and I had a soccer ball, would it naturally on its own just gently roll up that hill? No, okay? Do you agree that I have to force it by doing what? Lots of energy. Okay? Well, let's take the opposite effect. What if I'm standing at the top of that hill? What's probably going to happen? It's going to roll down. However, this is the important part, and I'm kind of going to the other side. Spontaneous. If the ball is sitting still, will it roll down the hill? Shut up. I don't care about you, ESPN. Say it again. Probably. Here's the deal. Is yours going off too? So here's the deal. Because it's spontaneous, does it mean it can happen without energy? That ball sitting there is not just going to say, oh, hi, there's a hill, let's roll down it, okay? If you're a 4-year-old, you might. But the ball needs some sort of energy, right? So, spontaneous still requires some, and again, that's the key, some energy. Let me go back to that match example. If you strike a match, does it burn with very little energy? All the matches in the box just naturally combust because they feel like being set on fire? No. Do you have to supply a minute amount of energy? Yes. Same concept with the ball on the hill. You got to give it a little kick, but not a lot is required. Yes, sir. Yes. But at some point, if that ball is sitting on a level plane, yeah, but yes, but what you're saying, yes, gravity is a form of energy. It's not heat energy, but it is energy. Okay? Now, so exothermic system loses energy to the surroundings. This delta H is less than 0. So just in case you happen to see it from that perspective, that's what it means. The delta H is negative. Again, it could get hot, but it's all based on perspective, and it is spontaneous. Again, do spontaneous things still require energy? Yes, go ahead. Like, yes. And here's the thing about that. From that perspective, I want you to think about it from this. Is the gas station burning an example of a chemical reaction? Yes. All right. Since it's a chemical reaction, all reactions have two parts. What are the two parts of a reaction? We're going to get to this, but since you've already asked, I'll go ahead and jump there. What are the two parts of a reaction? And the products. So, reactants react to make products. Well, what happens when you run out of reactants? You can't make any more products. So eventually, will the gas station run out of gasoline to burn? That's when the energy subsides. So when you are out of something to do, when you're out of whatever it is you're trying to work with, yes, the energy will subside. Okay, but where has all that energy gone? To the surroundings. Okay, all right. So let's look at it from two different perspectives. We've looked at it. We've talked about what energy is. We've talked about how it goes in and how it goes out. But let's get into the perspectives of exactly what it means. So let's look at the physical process and let's look at the chemical process of it. So as far as the physical process, here's what I want you to think. Do me a favor. Above this, write the word karate. Actually, pause. Don't write that there. Yeah, erase that. We're going to come back to karate in just a second. I'm gonna take the mic off, but I'm gonna keep recording, so hopefully it'll catch all this. So, lower energy is associated with particles. Now, when I say particles, what am I referring to? Atoms and molecules. Okay. Lower energy is associated with atoms and molecules being closer together. So let me give you a real life example. All right. So, Mason. If I wanted to have a conversation, if I was a point where it takes so much amount of energy to keep things together that we don't want to do that. Okay? So lower energy associated with things closer together. Mentally, visually, does that make sense? Good, because we're going to get into that later on as well. So this example I'm not really a big fan of, but I left it in here anyways. It says a pin on the ground versus the air. So what is pulling this pin back to the earth? Gravity. The farther this pin gets from the center of the earth, the harder gravity has to work to pull it back down. So again, right here versus on the ground, there's not a whole lot of difference. But if you take an airplane and you lift it off the ground and go 30,000 feet in the air, gravity's going to work really hard to get that thing back to the ground. Okay, that's why planes can't stop in midair. That's why they have to keep moving. So that is what's going on. So the more energy in the air because the force of gravity is enacting upon it. So the distance creates higher forms of energy. Okay? All right, so physical process. This is where I want you to write karate. Above this. Matter of fact, write karate board. Karate. However you spell it. You can write kung fu if you want to write kung fu. Okay. So let me give you a real world example before I explain this slide. So if I were to bring in a board in front of you and I said, here, break this board. We're not breaking your hand, hopefully. Okay. How would you break the board in terms of energy and the board? Not your body. Energy and the board. Okay. Very good. Say that key word again, the I word. No, the I word. Into the board. So when you transfer enough energy into the board, what happens? Hopefully it will break. The board, not your hand. Okay? So that's the whole goal here. The part that I want you to focus on right now is when you break the board, is it still a board? It's just a smaller board, right? You've got two smaller pieces. So what type of change is that? Physical or chemical? Physical. So this is where we're starting. So physical process. If it's endothermic, remember, what does the prefix endo mean? In or within. So endothermic, energy is in. Particles being closer together do what? Highlight that. They get pushed further apart. So we're talking more on the macro scale than the micro scale with a karate board. Okay? But if I separate that board using energy, that's an endothermic process. Okay? Did the board absorb energy? Yes. The board absorbed it. Now, we could get into the physics of every action there's an opposite but equal reaction. Did the board deliver some energy back into your hand? Yes, because that's how you break those bones if it's just enough. Okay? Now, here are some examples of things that are physical that have a positive delta H. And again, remember, positive means endothermic. Now, the first thing I want you to write, and I'm going to write it kind of crooked, but all of these things are changes in state of matter. And again, I apologize about how I'm having to write that. Changes in state of matter. All four of those things. Again, we've talked about this before. This is the number one most missed concept of this topic, is when you see these words, you think, okay, well, if it's boiling, that's a chemical change because I don't see it anymore. But we've talked about it. Is water still water even if you boil it? Yes, so let's talk about these things physically. So, melting. What's happening physically on the state of matter scale in something that's melting? Okay, solid to a liquid. So my question to you is, are those particles closer together or farther apart? How did you get them farther apart? It's absorbing energy. Okay? Evaporation was happening. Okay, liquid to gas. Closer together or farther apart? Farther apart. How? Energy went in. Boiling. Liquid to gas. Sublimation is solid to gas. So if you notice, All of these things are from close to far. Every single one of them. They're really close, and we're going to separate them. We're going to push them apart. And the way we push them apart is by adding energy into the system. From close to far. And I cannot stress to you how important this concept is from a physical and a chemical standpoint. From just understanding that when we put energy in, things must separate. Okay? So, if endothermic pushes things apart and absorbs energy, how can we write something that is the opposite of this? Exothermic must mean it does what? It puts things together. Okay? So think about this. If you have two atoms or two molecules that slam together, what are they releasing? And don't say sound. Okay, releasing energy. Now, is sound a form of energy? Yes, it's a vibrational form of energy that makes your ears vibrate. Okay, but when two things, now, I hate this word right here, even though I'll leave it in there. Pull. Does it necessarily have to be pulled closer together? No, because it can be forced closer together. So when things slam into each other, what is released? Energy. Okay? Essentially. Last two things. Condensation. It's going from what to what? Very good. Two more things. Stay with me. Stay with me. We're almost out of time. Freezing. What's happening? There's one more that I want you to write. Does anyone know what it's called to go from a gas to a solid? Deposition. Write that down. Deposition, and that is a gas to a liquid. Can water do that? Okay, I'll get her some in just a minute. Okay, it can. In the atmosphere, if it gets cold enough, those water vapor molecules can actually crystallize and freeze. If you've ever been flying and it gets really cold, it'll actually crystallize on the outside of the airplane. It kinda, yeah. Thank you. Don't forget your iPod.